729 trillion miles away, a telescope has tasted the air of another world and found something that should not exist. The James Webb Space Telescope detected a chemical signature in the atmosphere of planet K2-18b that on Earth is produced only by living creatures. We are about to journey to an alien ocean world 8 times more massive than our planet, explore the revolutionary technology that can smell the breath of distant worlds, and discover what this groundbreaking detection means for life in the universe. If you're ready to explore the strongest evidence yet for alien life, smash that like button and subscribe for more cosmic discoveries. Prepare yourselves. We begin. Deep in the data streams flowing from humanity's most powerful space telescope, a pattern emerged that made astronomers around the world hold their breath. The signal came from K2-18, a world so distant that light from our sun would take 124 years to reach it. Yet, somehow, the James Webb Space Telescope had managed to capture the chemical fingerprint of this alien atmosphere with unprecedented precision. Hidden within the spectral data was something extraordinary, a molecule called dimethyl sulfide that had never been detected on any planet outside our solar system. Scientists at Cambridge University first noticed the anomaly while analyzing wavelengths of infrared light. The telescope had observed K2-18b as it passed in front of its star, and during those precious moments, starlight filtered through the planet's atmosphere like sunlight through morning mist. Each molecule in that alien air absorbed specific colors of light, leaving dark lines in the spectrum like a cosmic barcode. But this barcode contained information that sent shockwaves through the scientific community. Among the familiar signatures of water vapor and carbon dioxide was a pattern they recognized from Earth's own oceans. Dimethyl sulfide produces a distinctive spectral fingerprint, and there it was, clear as day, in the atmosphere of a world nearly 800 trillion miles from home. The detection reached what scientists call 3 sigma statistical significance, meaning there was only a 0.3% chance that this signal occurred by random noise. Think of it like finding a specific grain of sand on a beach the size of Texas. The odds of this being a false positive were vanishingly small, yet the implications were staggering. Professor Niku Madhusudan, who led the research team, described the moment of discovery as seeing something that fundamentally changed our understanding of what might be possible in the universe. His team had used Webb's mid-infrared instrument to peer deeper into this alien world than ever before, and what they found challenged everything we thought we knew about life beyond Earth. The molecule they detected is not some exotic chemical found in the depths of space. On our planet, dimethyl sulfide is produced exclusively by living organisms, primarily tiny marine creatures called phytoplankton that float in Earth's oceans. These microscopic organisms pump out dimethyl sulfide as they live and die, creating a chemical signature that has never been observed through any non-biological process. Finding the same chemical signature on K2-18b was like discovering a familiar song playing on an alien radio station. The implications were immediately clear to the research team. Either this distant world harbors some form of life, or there are unknown chemical processes occurring in space that we have never encountered before. The data was so compelling that it prompted immediate follow-up observations using different instruments aboard the Webb telescope. Each new measurement confirmed what they had initially detected, building a case that this signal was real, persistent, and unlike anything previously observed in an exoplanet's atmosphere. But this was just the beginning of a discovery that would revolutionize our understanding of life in the cosmos. Imagine a world where endless oceans stretch beneath skies thick with hydrogen, and you begin to understand the alien nature of K2-18. This is not Earth. This planet weighs 8 6/10 times more than our homeworld and spans 2 6/10 times wider. If you could somehow stand on its surface, the crushing weight would be nearly 9 times what you experience right now. The gravity would pin you to the ground like an invisible hand pressing down with the weight of 8 people stacked on your shoulders. K2-18b orbits a red dwarf star in the constellation Leo, a cosmic lighthouse burning cooler and dimmer than our Sun. The planet completes its entire year in just 33 Earth days, racing around its star at a distance closer than Mercury orbits our Sun. Yet, because its star burns so much cooler, this alien world sits squarely in what astronomers call the habitable zone, that perfect distance where water can exist as a liquid. But here's where K2-18b becomes truly extraordinary. Scientists believe this world is completely covered by a global ocean that could be hundreds of miles deep. Picture Earth's oceans, then imagine them extending across every continent, every mountain range, every inch of the planet's surface. These alien seas would dwarf our deepest ocean trenches, creating a water world unlike anything in our solar system. Above this endless ocean hangs an atmosphere dominated by hydrogen gas. While Earth's air is mostly nitrogen and oxygen, K2-18 breathes hydrogen, the same gas that fills party balloons and powered the first hydrogen bombs. This creates atmospheric conditions so alien that we have no direct comparison in our solar system. Astronomers have classified K2-18b as a Hycean world, a term combining hydrogen and ocean to describe this new category of potentially habitable planets. Think of it as a cosmic hybrid, part gas giant, part water world, creating environmental conditions that could theoretically support life forms completely unlike anything we know on Earth. The planet receives roughly the same amount of energy from its star as Earth receives from the Sun, despite being much closer to its host star. This cosmic coincidence occurs because red dwarf stars burn at only about half the temperature of our Sun. It's like standing near a campfire versus a blast furnace. You can get the same warmth at very different distances. Temperature readings from the Webb telescope suggest K2-18b maintains conditions where liquid water could exist at the surface, with global temperatures potentially similar to Earth's. But the crushing atmospheric pressure and hydrogen-rich air would create an environment so hostile to human life that we could never survive there without protective technology. These are the conditions where dimethyl sulfide was detected, floating through alien skies above endless oceans on a world that operates by completely different rules than our own. Yet somehow, in this alien environment, a chemical signature emerged that we recognize from the microscopic life teeming in Earth's seas. In the vast catalogue of molecules floating through space, dimethyl sulfide stands apart as one of the most significant chemical signatures astronomers could possibly detect. On Earth, this molecule tells a story of life. Every breath of ocean air carries traces of dimethyl sulfide, released by countless trillions of microscopic marine organisms as they live, reproduce, and die in our planet's seas. These tiny creatures, phytoplankton barely visible to the naked eye, pump out dimethyl sulfide as a natural byproduct of their biological processes. Think of dimethyl sulfide like the exhaust from a living engine. Just as a car-burning gasoline produces carbon monoxide and water vapor, living organisms processing sulfur compounds in seawater naturally create dimethyl sulfide. The molecule then escapes into the atmosphere, where it plays a crucial role in cloud formation and Earth's climate system. But here's what makes this discovery on K2-18b so revolutionary. Scientists have never identified any non-biological process that can produce dimethyl sulfide in the concentrations detected by the Webb telescope. After decades of studying atmospheric chemistry, geochemistry, and planetary processes, researchers have found no known geological or chemical mechanism that could create this molecule without the involvement of living organisms. The detection on K2-18b showed concentrations of dimethyl sulfide thousands of times stronger than what we typically measure in Earth's atmosphere. This creates a fascinating puzzle. If biological processes on Earth produce only tiny amounts that quickly break down in our atmosphere, how could this alien world maintain such high concentrations without an even more robust biological source? Dr. Niku Madhusudan, the lead researcher on this discovery, explained that dimethyl sulfide essentially acts like a chemical fingerprint of life. Just as your unique fingerprint can identify you among billions of people, the presence of dimethyl sulfide in an atmosphere could identify biological activity among billions of worlds. The molecule consists of one sulfur atom bonded to two carbon atoms, each of which connects to three hydrogen atoms. This simple arrangement, carbon, hydrogen, and sulfur, creates a chemical structure that life on Earth has learned to manufacture, but that doesn't occur naturally through geological processes. What makes the K218b detection even more compelling is that dimethyl sulfide breaks down relatively quickly when exposed to ultraviolet radiation from stars. This means the molecule must be constantly replenished to maintain the levels observed by Webb. It's like finding fresh footprints in the snow. Something active must be creating them recently and continuously. The research team used Webb's mid-infrared instrument to detect dimethyl sulfide by analyzing how the molecule absorbs specific wavelengths of infrared light. Each molecule has a unique absorption signature, like a cosmic fingerprint that shows up when starlight passes through an atmosphere containing that chemical. Finding this signature in the skies of K218b was like discovering a message written in a language we recognize, transmitted across the vast darkness of interstellar space. A message that, if confirmed, would prove we are not alone. The James Webb Space Telescope doesn't just see distant worlds, it tastes their atmospheres across trillions of miles of empty space. Imagine trying to analyze the ingredients in a cake by smelling it from 100 miles away, and you begin to understand the incredible precision required for Webb's atmospheric detective work. This 21-foot-wide golden mirror operates in the frigid depths of space, cooled to nearly absolute zero, where it can detect the faintest whispers of heat radiating from alien worlds. Webb accomplishes this seemingly impossible feat through a technique called transmission spectroscopy. When K218b passes in front of its star as seen from Earth, starlight filters through the planet's atmosphere like sunlight streaming through a stained glass window. Each molecule in that alien air absorbs specific colors of light, creating dark lines in the spectrum that act like a chemical barcode. The telescope's mid-infrared instrument, known as MIRI, operates in wavelengths of light invisible to human eyes. While we see visible light wavelengths measured in hundreds of nanometers, MIRI detects infrared radiation spanning 5 to 28 micrometers, wavelengths so long that 28,000 of them lined up would equal the width of a human hair. This infrared sensitivity provides Webb with a crucial advantage over previous telescopes. Molecules in planetary atmospheres have their strongest absorption signatures in the infrared spectrum, meaning Webb can detect chemicals that remain completely invisible to optical telescopes. It's like having superhuman vision that can see heat signatures through walls. The precision required for these measurements defies comprehension. Webb must detect changes in starlight brightness of less than 1 part in 10,000, equivalent to measuring the difference in brightness between a car's headlight with and without a single sheet of tissue paper placed in front of it, while standing several miles away. To achieve this extraordinary sensitivity, Webb operates at a temperature of negative 370 degrees Fahrenheit, colder than the surface of Pluto. This extreme cooling eliminates thermal noise that would otherwise swamp the faint signals from distant exoplanets. The telescope essentially becomes a giant, ultra-sensitive thermometer floating in the vacuum of space. Webb's revolutionary capabilities extend beyond simple detection. The telescope can measure not just whether a molecule exists in an alien atmosphere, but how much of it is present. The strength of each absorption line directly correlates to the concentration of molecules creating that signature. This allows scientists to create detailed chemical inventories of worlds they will never visit. The K2-18b observations required Webb to stare at this distant star system for hours, collecting photons one by one as the planet crossed in front of its star. Each transit lasted only a few hours, during which the telescope gathered light that had traveled for 124 years across the galaxy to reach its sensors. This technological marvel transforms Webb into humanity's most powerful tool for exploring the chemical composition of alien worlds, capable of detecting the molecular signatures of life across the vast emptiness of interstellar space. But even this incredible technology has limitations that challenge our ability to confirm what we think we've found. In the unforgiving world of scientific discovery, finding something extraordinary is only the beginning. Proving it exists requires meeting the most demanding statistical standards in human knowledge. The dimethyl sulfide detection on K2-18b achieved what scientists call 3 sigma statistical significance, meaning there's only a 0.3% chance that this signal occurred by random noise or instrument error. In everyday terms, this would be like flipping a coin and getting heads 333 times in a row. Technically possible, but so unlikely that most people would bet their life savings on the pattern being real. But science demands more than most people would believe it. The gold standard for scientific discovery requires 5 sigma significance, a threshold so stringent that there's only a 1 in 3 and a flagrant or less 500,000 chance of the result being a false positive. Think of it as the difference between being 99% sure and being 99.9997% certain. This statistical rigor exists because the history of science is littered with exciting discoveries that later prove to be measurement errors, instrument malfunctions, or wishful thinking. In 1996, scientists announced they had found evidence of ancient microbial life in a Martian meteorite, generating worldwide headlines. Decades later, most researchers believe those biosignatures were actually created by non-biological processes. The Webb Telescope team, led by Professor Niku Madhusudan, acknowledges their detection falls short of the 5 sigma threshold required to claim definitive proof of alien life. They describe themselves as cautiously optimistic, scientific code for "we think we found something incredible, but we need more evidence." Reaching 5 sigma significance for the K2-18b detection would require additional observation time with Webb, potentially 16 to 24 more hours of telescope time pointed at this distant world. In the competitive world of space telescope scheduling, where every minute of observing time is precious, securing this additional time represents a significant investment in confirming what could be the most important discovery in human history. The statistical challenge becomes even more complex when you consider that Webb is detecting these molecules across 729 trillion miles of space. The signal must travel through interstellar dust, cosmic radiation, and the telescope's own instrumental noise before reaching the detectors. Each of these factors introduces potential sources of error that could mimic a real detection. Independent research teams have already begun reanalyzing the Webb data using different statistical methods and atmospheric models. Some preliminary studies suggest the dimethyl sulfide signal might be even weaker than initially reported, while others support the original findings. This scientific debate represents the peer review process working exactly as intended, multiple teams challenging and verifying each other's work. The 3 sigma detection represents humanity's strongest evidence yet for possible alien life, but it also illustrates the enormous challenge of proving such an extraordinary claim. We stand at the threshold of potentially the most significant discovery in human history, yet the statistical requirements for certainty remain frustratingly out of reach. What hangs in the balance is nothing less than answering the fundamental question, are we alone? Beyond the familiar rocky planets and gas giants of our solar system lies a new category of worlds that could revolutionize our understanding of where life might flourish. Haitian planets represent a cosmic hybrid that combines the deep oceans of water worlds with the thick hydrogen atmospheres of mini-Neptunes. The name itself merges hydrogen and ocean, describing planets that operate by rules completely different from anything we know in our solar system. These worlds challenge our Earth-centric assumptions about what makes a planet habitable. K2-18b serves as the prototype for this new class of potentially life-bearing worlds. Unlike Earth, where life exists at the interface between a thin atmosphere and relatively shallow seas, Haitian planets create conditions where life could theoretically exist throughout vast three-dimensional ocean environments, hundreds of miles deep, all beneath crushing, hydrogen-rich atmospheres. Think of Haitian worlds as cosmic pressure cookers, where extreme conditions might actually favor certain types of life. The dense hydrogen atmosphere creates tremendous pressure at the ocean's surface, potentially hundreds of times greater than atmospheric pressure on Earth. Yet this same pressure could stabilize liquid water at temperatures where it would normally boil away into space. The hydrogen-rich atmosphere also provides unique chemical opportunities for life. On Earth, most organisms derive energy from processes involving oxygen, but hydrogen-based metabolisms could theoretically support entirely different forms of biology. Some Earth microbes already demonstrate this capability, thriving in deep-sea volcanic vents where they derive energy from hydrogen sulfide rather than sunlight. Professor Niku Madhusudan and his team theorized Haitian worlds as potentially habitable environments in 2021, predicting that such planets should produce detectable biosignature gases like dimethyl sulfide. The recent Webb telescope detection of exactly these predicted molecules on K2-18b provides strong support for the Haitian planet hypothesis. These worlds offer several advantages over Earth-like rocky planets when searching for signs of life. Their thick atmospheres make them much easier to study with current telescope technology, since atmospheric signals are stronger and more detectable. Additionally, Haitian planets are likely much more common than Earth-sized rocky worlds in habitable zones, potentially giving life many more opportunities to evolve throughout the galaxy. The sheer size of Haitian oceans creates another intriguing possibility. Earth's oceans contain about 1.3 billion cubic kilometers of water, but a Haitian world like K2-18b could harbor oceans hundreds of times larger. This vast volume would provide enormous space for life to evolve and diversify, potentially supporting complex ecosystems that dwarf anything on Earth. Temperature conditions on Haitian worlds could remain stable across their entire surfaces due to efficient heat transport through their thick atmospheres. Unlike Earth, where polar regions freeze while equatorial areas bake, Haitian planets might maintain relatively uniform temperatures suitable for life from pole to pole. The discovery of potential biosignatures on K2-18b suggests that Haitian worlds deserve serious consideration as we search for life beyond Earth. These alien oceans might represent our best chance of finding biology that operates by completely different rules than terrestrial life. But what kind of life could actually survive in such extreme alien environments? In the sunlit surface waters of Earth's oceans, trillions of microscopic organisms carry out a chemical process that may have just revealed itself on a world 124 light-years away. Phytoplankton, tiny marine plants barely visible to the naked eye, represent some of the most abundant life forms on our planet. A single drop of seawater can contain thousands of these microscopic organisms, each one a living chemical factory that transforms seawater minerals into the building blocks of ocean ecosystems. These creatures are so small that 50,000 of them could fit on the head of a pin, yet collectively they produce more oxygen than all of Earth's forests combined. When phytoplankton process sulfur compounds dissolved in seawater, they naturally produce dimethyl sulfide as a metabolic byproduct. Think of it like cellular breathing. Just as humans exhale carbon dioxide when our cells burn sugar for energy, phytoplankton release dimethyl sulfide when they process sulfur-containing nutrients from their marine environment. This biological process occurs on a staggering scale in Earth's oceans. Marine phytoplankton pump approximately 15 to 30 million tons of dimethyl sulfide into our atmosphere every year, enough to fill about 12,000 Olympic swimming pools with pure dimethyl sulfide gas. The molecule then rises into the atmosphere, where it plays a crucial role in cloud formation and global climate regulation. But here's what makes the K218b detection so significant. On Earth, dimethyl sulfide concentrations in the atmosphere typically measure less than 1 part per billion. The molecule breaks down quickly when exposed to sunlight, meaning it must be constantly replenished by living organisms to maintain even these trace levels. Despite this continuous biological production, atmospheric concentrations remain extremely low. The Webb telescope detected dimethyl sulfide on K218b at concentrations potentially thousands of times higher than anything measured in Earth's atmosphere. This suggests either an incredibly robust biological source constantly pumping out the molecule, or some unknown non-biological process that we have never observed in nature. Marine biologists have studied dimethyl sulfide production for decades, documenting how different species of phytoplankton create varying amounts of this molecule. Some species, particularly certain types of algae, produce dimethyl sulfide when stressed by changes in temperature, salinity, or nutrient availability. Others generate it as part of their normal cellular processes, regardless of environmental conditions. The connection between Earth's phytoplankton and the potential life on K218b raises fascinating questions about biological convergence. If life exists on this distant world, did it independently evolve similar metabolic processes that produce dimethyl sulfide? Or might there be some fundamental chemical advantage to this particular molecular pathway that makes it likely to emerge wherever life processes sulfur compounds? Research on extremophile organisms, Earth life that thrives in harsh conditions similar to those on Hycean worlds, shows that many can survive in high-pressure, hydrogen-rich environments. Some deep-sea microorganisms actually prefer conditions that would be instantly lethal to most surface life. These tiny connections between Earth's microscopic marine life and potential alien biology represent one of the most compelling aspects of the K218b discovery. Hidden within the ancient light of distant stars lies the recipe for reading the atmospheres of alien worlds, decoded through one of astronomy's most elegant detective techniques. Transmission spectroscopy transforms every exoplanet transit into a cosmic chemistry experiment. When K218b passed between its star and Earth, it created a natural laboratory where starlight served as the probe and the planet's atmosphere became the sample being analyzed. For a few precious hours, photons that had traveled across interstellar space carried with them the chemical signature of an alien world. The process begins with a fundamental property of matter. Every molecule absorbs light at specific wavelengths, like a unique barcode written in the language of physics. Water vapor absorbs strongly at certain infrared wavelengths, carbon dioxide at others, and dimethyl sulfide at its own characteristic frequencies. When starlight passes through a planetary atmosphere, each molecule present removes its specific colors from the light, leaving dark absorption lines in the spectrum. Think of it like looking at a distant streetlight through colored glass. If the glass is red, you'll see less blue light reaching your eyes. Similarly, when starlight filters through K218's atmosphere, molecules in that alien air selectively remove certain wavelengths, telling us exactly which chemicals float in those distant skies. The Webb telescope's revolutionary capability lies in its extraordinary sensitivity to these absorption signatures. Previous telescopes could detect only the strongest spectral features from the largest, hottest exoplanets. Webb can measure absorption lines so weak they change the total light from the star by less than 1 part in 10,000, like detecting whether someone turned off a single light bulb in a city viewed from space. During K2-18's transit, Webb compared the star's light spectrum when the planet was in front of the star to measurements taken when the planet was beside it. The difference between these two spectra revealed which wavelengths were absorbed by the planetary atmosphere. This differential measurement technique eliminates most sources of instrumental error and stellar variability. The detection of dimethyl sulfide required Webb to identify absorption features at wavelengths around 9 micrometers, invisible infrared radiation that carries 20 times less energy than visible light. At these wavelengths, dimethyl sulfide produces distinctive absorption patterns that cannot be easily confused with other atmospheric molecules. The precision required for this measurement challenges the limits of current technology. Detecting dimethyl sulfide on K2-18b was equivalent to measuring the thickness of a human hair from a distance of 10 miles, while accounting for atmospheric turbulence, instrumental vibrations, and cosmic radiation interfering with the signal. What makes transmission spectroscopy particularly powerful is its ability to provide quantitative measurements. The strength of each absorption line directly corresponds to the concentration of molecules creating that signature. Stronger absorption means more molecules. Weaker signals indicate lower concentrations. This allows astronomers to create detailed chemical inventories of alien atmospheres. The Webb observations revealed not just the presence of dimethyl sulfide on K2-18b, but estimated its abundance in that alien atmosphere. This quantitative capability transforms speculation about exoplanet atmospheres into precise measurements of their chemical composition. But transmission spectroscopy also revealed other crucial clues about this mysterious world. The dimethyl sulfide detection on K2-18b did not occur in isolation. It emerged as part of a complex atmospheric chemical story that transforms our understanding of this alien world. Webb's spectroscopic analysis revealed abundant methane and carbon dioxide in K2-18's atmosphere, two molecules that paint a detailed picture of environmental conditions on this distant world. These gases serve as atmospheric detectives, providing clues about temperature, pressure, and chemical processes occurring in those alien skies. Methane on K2-18b appears in concentrations much higher than what we observe in Earth's atmosphere. On our planet, methane exists primarily as a trace gas produced by biological processes like digestion in animals and decomposition by bacteria. But in the hydrogen-rich atmosphere of K2-18b, methane could form through entirely different mechanisms involving the planet's deep oceans and crushing atmospheric pressure. The simultaneous presence of methane and carbon dioxide creates what atmospheric chemists call a reducing environment, conditions where chemical reactions favor the formation of hydrogen-rich compounds. This environment could theoretically support metabolic processes completely different from Earth's oxygen-based biology, potentially explaining how life might survive in K2-18's alien atmosphere. Carbon dioxide detection provides crucial information about the planet's ocean chemistry. On Earth, our oceans absorb enormous quantities of carbon dioxide from the atmosphere, regulating global climate through complex chemical buffering systems. The carbon dioxide observed on K2-18b suggests similar ocean-atmosphere interactions might be occurring on this distant world, potentially indicating vast bodies of liquid water beneath its hydrogen-rich sky. What makes this atmospheric composition particularly intriguing is what's missing: ammonia. Earth's early atmosphere contained significant amounts of ammonia, But K2-18b shows virtually no detectable ammonia, despite conditions that should theoretically produce this molecule through non-biological processes. The absence of ammonia supports the hypothesis that K2-18b harbors deep oceans where ammonia would dissolve readily, removing it from the atmospheric inventory. This chemical combination, abundant methane and carbon dioxide with absent ammonia, matches theoretical predictions for Hycean worlds with global oceans beneath hydrogen atmospheres. It's like finding puzzle pieces that fit together to reveal a picture of an alien water world operating by its own unique chemical rules. The methane to carbon dioxide ratio observed on K2-18b also provides clues about energy sources available for potential life. On Earth, many microorganisms derive energy by converting methane to carbon dioxide in processes called methanotrophy. If similar biological processes occur on K2-18b, they could represent an entirely different pathway for life to extract energy from its environment. Temperature measurements derived from these molecular detections suggest K2-18b maintains surface conditions where liquid water could exist, despite its location close to its red dwarf star. The greenhouse effects of methane and carbon dioxide, combined with heat transport through the dense hydrogen atmosphere, create a complex climate system that could stabilize temperatures suitable for liquid oceans. These atmospheric clues converge to paint K2-18b as a world where chemistry operates in ways we're only beginning to understand, and where conditions might support forms of life, unlike anything in our terrestrial experience. The pieces of evidence point towards something extraordinary lurking in those alien skies. The star that K2-18b calls home burns with the dim red glow of cosmic longevity, creating conditions that could make life around such stars far more common than we ever imagined. Red dwarf stars like K2-18 represent the universe's ultimate survivors. These stellar lighthouses burn hydrogen fuel so efficiently that they can continue shining for trillions of years, longer than the current age of the universe, by a factor of nearly 100. While our sun will exhaust its nuclear fuel in about 5 billion years, red dwarfs will still be burning bright when the last black holes evaporate in the distant future. This extraordinary longevity creates unique opportunities for life. On planets orbiting red dwarfs, biological evolution would have trillions of years to develop, experiment, and diversify. Earth's life has had only 4.5 billion years to evolve from simple bacteria to complex ecosystems. Imagine what forms of life might emerge given 200 times longer to develop and adapt. K2-18b orbits its red dwarf star at a distance of only 13 million miles, roughly 1/7 the distance between Earth and our Sun. At this proximity around a sun-like star, any planet would be instantly vaporized by intense radiation. But red dwarfs burn at only about half the surface temperature of our Sun, allowing planets to maintain liquid water at much closer orbital distances. This close proximity creates what astronomers call tidal locking, the same gravitational forces that keep our moon always showing the same face to Earth. One hemisphere of K2-18b always faces its star in permanent daylight, while the other side remains locked in eternal darkness. You might expect this to create impossible temperature extremes, but the planet's thick hydrogen atmosphere could transport heat from the day side to the night side, potentially creating stable global temperatures. Red dwarf habitable zones also remain stable for incredibly long periods. Our Sun gradually increases in brightness as it ages, meaning Earth's habitable zone slowly moves outward over geological time. In contrast, red dwarfs maintain nearly constant energy output for trillions of years, providing stable, habitable conditions that could support life indefinitely. The universe contains roughly 75% red dwarf stars, making them the most common type of star in the Milky Way galaxy. If planets around red dwarfs can indeed harbor life, it would multiply the potential number of habitable worlds by orders of magnitude. Instead of focusing our search on the rare sun-like stars, we could explore billions of red dwarf systems for signs of biology. K2-18b receives approximately the same amount of energy from its red dwarf star as Earth receives from our Sun, despite being much closer to its host star. This energy balance creates surface temperatures potentially suitable for liquid water oceans, the foundation requirement for life as we understand it. The detection of potential biosignatures around K2-18's red dwarf star suggests that these dim, long-lived stellar furnaces might represent our best targets in the search for alien life. But confirming life around red dwarfs requires us to solve an atmospheric mystery that challenges our understanding of planetary chemistry. Sometimes the most important discoveries come not from what we find, but from what's conspicuously absent from where it should be. In the complex chemistry of K2-18's atmosphere, one molecule that should be abundant is virtually nowhere to be found: ammonia. This absence tells a story more compelling than many positive detections, providing crucial evidence that this alien world harbors the deep oceans necessary to support life. Ammonia represents one of the most fundamental building blocks in planetary atmospheric chemistry. Under the temperature and pressure conditions that exist on K2-18b, chemical models predict that ammonia should form readily through reactions between hydrogen and nitrogen in the atmosphere. The planet's hydrogen-rich environment provides ideal conditions for ammonia production, yet Webb's sensitive instruments detect virtually none of this expected molecule. Think of the missing ammonia like a dog that didn't bark in a mystery novel. Its absence provides the key clue to solving the puzzle. If K2-18b was simply a gas planet with no surface oceans, its atmosphere should contain significant amounts of ammonia alongside the methane and carbon dioxide that Webb detected. The fact that ammonia is missing suggests something is actively removing it from the atmospheric inventory. The most plausible explanation involves vast oceans beneath K2-18's hydrogen atmosphere. Ammonia dissolves readily in liquid water, especially under the high-pressure conditions that would exist on this alien world. If K2-18b harbors global oceans hundreds of miles deep, these waters would act like enormous chemical sponges, absorbing ammonia from the atmosphere and preventing it from accumulating in detectable concentrations. This chemical absorption process occurs on Earth as well, where our oceans contain dissolved nitrogen compounds that would otherwise exist as atmospheric ammonia. But K2-18's much deeper oceans and higher atmospheric pressures would create an even more efficient ammonia removal system, explaining why Webb's instruments find so little of this molecule in the planet's air. The missing ammonia also supports the Hycean world hypothesis in another crucial way. Theoretical models of hydrogen-rich planets with surface oceans predict exactly this atmospheric composition: abundant methane and carbon dioxide with depleted ammonia levels. Finding this specific chemical fingerprint provides strong evidence that K2-18b matches the theoretical predictions for an ocean world beneath a hydrogen sky. Dr. Subhajit Sarkar, a member of the research team, described the ammonia absence as a smoking gun for the presence of liquid water on K2-18's surface. The chemical evidence suggests not just the presence of oceans, but oceans deep enough and extensive enough to significantly alter the planet's atmospheric chemistry through dissolution processes. This atmospheric detective work illustrates how exoplanet science has evolved beyond simply cataloging which molecules exist on distant worlds. Modern atmospheric analysis can reveal the complex interactions between planetary surfaces, oceans, and atmospheres across trillions of miles of space, providing detailed insights into environmental conditions on worlds we will never visit. The missing ammonia mystery transforms K2-18b from an interesting exoplanet into a world where chemistry tells the story of vast alien seas beneath foreign skies. But not everyone in the scientific community accepts this compelling chemical evidence. In the high-stakes world of astrobiology, the difference between discovering alien life and announcing a false positive could determine the credibility of an entire scientific field for generations. The dimethyl sulfide detection on K218b has sparked intense debate within the astronomical community, dividing scientists between those who see compelling evidence for life and skeptics who demand extraordinary proof for extraordinary claims. This scientific tension represents the peer review process working exactly as intended, with multiple teams challenging and scrutinizing every aspect of the discovery. Dr. Jake Taylor from Oxford University performed an independent reanalysis of Webb's K218b data using different statistical methods and atmospheric models. His analysis suggested the dimethyl sulfide signal might be significantly weaker than originally reported, potentially falling within the range of instrumental noise rather than representing a genuine atmospheric detection. Taylor's work illustrates how different approaches to data analysis can yield conflicting results from identical observations. The challenge lies in the incredible difficulty of detecting molecules across 729 trillion miles of space. Every photon that reaches Webb's detectors has traveled for 124 years through cosmic dust, radiation fields, and gravitational influences that could potentially alter or obscure the spectral signatures astronomers are trying to measure. The margin for error becomes razor-thin when dealing with signals this faint and distant. False positives have haunted astrobiology throughout its history. The famous Martian meteorite announcement in 1996 generated worldwide headlines when scientists claimed to have found microscopic fossils in a rock blasted off Mars billions of years ago. Decades of subsequent research suggested these biosignatures were more likely produced by non-biological mineral processes, serving as a cautionary tale about the dangers of premature announcements. Professor Sarah Seeger from MIT, a leading exoplanet researcher, described the K218b detection as not yet a biosignature, but a timely prompt to sharpen our methods and expectations. Her assessment reflects the scientific community's increased caution following previous false alarms, emphasizing the need for multiple independent confirmations before claiming discovery of alien life. The dimethyl sulfide controversy also highlights fundamental questions about what constitutes sufficient evidence for biosignatures. Should scientists require 5 sigma statistical significance, the gold standard for particle physics discoveries? Or might the profound implications of finding alien life justify accepting lower thresholds of certainty, balanced against the risk of false positives? Some researchers argue that unknown chemical processes might exist in the extreme environments of Hycean worlds, potentially producing dimethyl sulfide through geological mechanisms we haven't yet discovered. The crushing pressures, hydrogen-rich atmospheres, and deep ocean chemistry of planets like K218b create conditions that don't exist anywhere in our solar system, making it difficult to rule out non-biological explanations definitively. Dr. Eddie Schwieterman from UC Riverside noted that the best biosignatures on an exoplanet may differ significantly from those we find most abundant on Earth today. This perspective suggests that our Earth-centric understanding of biosignatures might blind us to legitimate signs of alien life that operate by different biological rules. The scientific debate continues as researchers worldwide scrutinize every aspect of the Webb telescope data, searching for the truth hidden within those distant photons. In the demanding arena of scientific discovery, crossing the 5 sigma threshold represents the difference between suggestive evidence and proof that reshapes human understanding of the universe. 5 sigma significance means there's only a 1 in 3.5 million chance that the observed signal occurred by random fluctuation rather than representing a genuine discovery. To put this in perspective, you're more likely to be struck by lightning twice in the same year than to see a 5 sigma result occur by pure chance. This extraordinarily high bar exists because science has learned painful lessons about the consequences of announcing discoveries that later prove false. The Large Hadron Collider used 5 sigma significance as the threshold for announcing the discovery of the Higgs boson in 2012, a detection that required analyzing trillions of particle collisions and years of data collection. The gravitational wave detections by LIGO also met 5 sigma standards before announcing that ripples in spacetime had been detected from colliding black holes billions of light-years away. But applying particle physics standards to exoplanet atmospheric chemistry creates unique challenges. Unlike controlled laboratory experiments where scientists can repeat measurements thousands of times, exoplanet observations depend on rare transit events that occur only when planetary orbits align perfectly with Earth's viewing angle. K2-18b transits its star just once every 33 days, making rapid confirmation studies impossible. The current 3 sigma detection of dimethyl sulfide on K2-18b falls short of the 5 sigma gold standard, creating a scientific limbo where the evidence is compelling but not conclusive. Reaching 5 sigma significance would require additional Webb telescope observations, totaling 16 to 24 hours of precious observing time, a significant investment in confirming what could be the most important discovery in human history. Professor Niku Madhusudan and his team acknowledge this statistical gap, while arguing that the public deserves to know about potential alien life discoveries as they develop, rather than waiting years for absolute confirmation. Madhusudan compared the situation to NASA announcing Mars rover missions before they successfully land. We celebrate the attempt and possibility, while acknowledging uncertainty about the outcome. The 5 sigma requirement also creates philosophical tensions within astrobiology. Some researchers argue that the profound implications of discovering alien life justify accepting lower statistical thresholds, especially when multiple independent lines of evidence support the same conclusion. Others insist that extraordinary claims require extraordinary evidence, regardless of the discovery's potential significance. Independent verification represents another path toward building confidence in the K2-18b detection. When multiple research teams using different instruments, analytical methods, and atmospheric models reach similar conclusions, the combined evidence can approach 5 sigma significance even if individual studies fall short of this threshold. The Webb telescope's upcoming observations of K2-18b, using different instruments and longer integration times, could provide the additional data needed to either confirm the dimethyl sulfide detection at 5 sigma confidence or definitively rule it out as instrumental noise. Until that threshold is crossed, humanity remains suspended between 2 possibilities. We have detected the first confirmed signs of alien life, or we have encountered the most convincing false positive in the history of astrobiology. The answer lies hidden in photons, yet to be collected from a distant world. In the crushing depths of K2-18's alien oceans, life faces challenges that would instantly destroy any organism from Earth. Yet these same extreme conditions might nurture biology beyond our wildest imagination. Forget everything you think you know about what life looks like. The creatures that might inhabit K2-18b would exist in an environment so alien that they could be producing dimethyl sulfide through biological processes completely unlike anything in Earth's oceans, under pressures hundreds of times greater than our deepest ocean trenches, surrounded by hydrogen-rich water beneath skies that rain exotic chemistry. Alien life would have evolved solutions to problems terrestrial biology never faced. These hypothetical organisms might exist as vast floating colonies distributed throughout K2-18's 3-dimensional ocean environment. Without a solid surface to anchor against, life might have evolved elaborate internal structures to maintain position in the crushing depths. possibly using hydrogen-filled bladders or magnetic navigation systems to traverse their liquid world. The absence of sunlight in K2-18's deep oceans would eliminate photosynthesis as an energy source, forcing alien life to derive power from chemical processes involving the planet's abundant hydrogen, methane, and dissolved minerals. Think of organisms that function like living fuel cells, extracting energy from the chemical differences between various depth layers in their global ocean. Size scales for K2-18b life might dwarf anything on Earth. With unlimited three-dimensional space and no surface gravity constraints, alien organisms could grow to tremendous sizes while maintaining structural integrity through internal pressure regulation. Imagine jellyfish-like creatures spanning miles across, drifting through hydrogen-rich seas while processing chemicals on a scale that makes Earth's whale populations look microscopic. The high-pressure environment might favor life forms with radically different biochemistry than Earth organisms. Where terrestrial life uses water as a biochemical solvent, K2-18b life might employ hydrogen-rich solutions that remain liquid under extreme pressures and temperatures. These alien biochemistries could produce dimethyl sulfide as part of metabolic processes we've never encountered. Communication between organisms in K2-18's dense fluid environment might involve chemical signaling through dimethyl sulfide and related compounds. Rather than producing these molecules as waste products, alien life might use them as a sophisticated biochemical language, creating the concentrated atmospheric signals detected by Webb as a byproduct of planetary-scale communication networks. Reproduction and evolution in this alien environment could operate on timescales completely different from Earth life. With red dwarf stars providing stable energy for trillions of years, K2-18b organisms might have evolved reproductive cycles spanning thousands or millions of years, creating biological complexity that makes Earth's ecosystems look simple by comparison. The creatures might exist in vertical layers throughout the ocean depths, with different species specialized for different pressure zones and chemical environments. Surface organisms might process atmospheric hydrogen directly, while deep ocean life forms could derive energy from geological processes occurring at the ocean floor hundreds of miles below. If life exists on K2-18, it represents biology, operating by rules we're only beginning to imagine, organisms that have solved the challenge of existence in conditions that would be instantly lethal to every known form of terrestrial life. Yet somehow, across the vast darkness of space, they might be producing the same molecular signature we recognize from Earth's microscopic marine organisms. 729 trillion miles, a number so vast that light itself, traveling at 186,000 miles per second, takes 124 years to bridge the gap between K2-18b and Earth. To comprehend this distance, imagine scaling down the entire journey to something more manageable. If Earth were the size of a grain of sand, K2-18b would be located roughly 4,000 miles away, the distance from New York to Rome. Yet somehow, the James Webb Space Telescope managed to detect individual molecules in that distant world's atmosphere with precision that defies human comprehension. The photons carrying information about dimethyl sulfide on K2-18b began their journey when Abraham Lincoln was president. These packets of electromagnetic energy traveled through interstellar space for longer than human civilization has existed, passing through cosmic dust clouds, gravitational fields of unseen objects, and radiation from countless other stars, before finally reaching Webb's golden mirror. During their epic journey, these photons encountered obstacles that could have destroyed or altered the very information astronomers needed to detect alien life. Interstellar dust grains, each smaller than particles in cigarette smoke, can scatter and absorb specific wavelengths of light. Magnetic fields threading through space can rotate the polarization of electromagnetic radiation, Even the gravitational influence of dark matter clumps could theoretically bend light paths and alter spectral signatures. The Webb telescope had to account for all these potential sources of contamination while extracting the incredibly faint signal of dimethyl sulfide from K2-18's atmosphere. The molecular absorption signature represented a change in starlight brightness of less than 1 part in 10,000, equivalent to detecting whether someone turned off a single candle in a chandelier viewed from the surface of the Moon. Webb's location at the 2 Lagrange point, 1 million miles from Earth, was chosen specifically to minimize interference from our planet's atmosphere and thermal radiation. Even at this remote location, the telescope operates in a cosmic shooting gallery of micrometeorites, charged particles from solar wind, and high-energy cosmic rays that can create false signals in its sensitive detectors. The precision required for the K2-18b detection challenges the fundamental limits of measurement across interstellar distances. Each individual photon reaching Webb's instruments carries only infinitesimal amounts of information, requiring the telescope to collect light for hours to build up sufficient signal strength to detect molecular absorption features. Temperature fluctuations of just a few thousandths of a degree could swamp the dimethyl sulfide signal, forcing Webb to maintain incredible thermal stability while floating in the vacuum of space. The telescope's instruments operate at temperatures colder than Pluto's surface, achieved through complex cooling systems that must function flawlessly for years without maintenance. Despite these seemingly impossible challenges, Webb successfully detected not just dimethyl sulfide, but created detailed chemical inventories of K2-18's atmosphere, including methane, carbon dioxide, and water vapor. This achievement represents one of the most technically demanding measurements in the history of astronomy. The fact that we can detect potential signs of alien life across such mind-boggling distances speaks to both the incredible sensitivity of modern space telescopes and the fundamental universality of physical laws that govern light and matter throughout the cosmos. Yet this remarkable technical achievement has not silenced critics who question whether we're truly seeing signs of life. In the aftermath of the K2-18b announcement, a growing chorus of scientists has emerged with a sobering message. Extraordinary claims require extraordinary evidence, and this discovery may not meet that standard. Dr. Kevin Stevenson from Johns Hopkins University describes the overwhelming consensus among his exoplanet colleagues that enthusiasm exceeded the strength of evidence in the dimethyl sulfide detection. His assessment reflects deeper concerns within the scientific community about the dangers of premature announcements that could damage public trust in science if later proven false. The skepticism gained momentum when multiple independent research teams attempted to reproduce the Webb telescope findings using the same data but different analytical approaches. Several of these reanalyses failed to confirm the dimethyl sulfide detection, instead finding signals consistent with instrumental noise rather than genuine atmospheric chemistry. These conflicting interpretations highlight how subtle differences in data processing can lead to dramatically different conclusions. Dr. Jake Taylor's reanalysis at Oxford University proved particularly influential among skeptics. Using standard exoplanet analysis techniques widely accepted in the field, Taylor found the data is consistent with a flat line, rather than showing the molecular absorption features claimed by the Cambridge team. His work suggested that more sophisticated statistical methods might be revealing patterns in noise rather than detecting real atmospheric signatures. The controversy extends beyond statistical arguments to fundamental questions about atmospheric chemistry. Some researchers point out that the Webb observations failed to detect ethane, a molecule that should accompany dimethyl sulfide if it were being broken down by ultraviolet radiation from K2-18's star. The absence of expected byproducts raises questions about whether the dimethyl sulfide detection represents genuine atmospheric chemistry or instrumental artifacts. Professor Laura Kreidberg from the Max Planck Institute emphasized that the strength of evidence depends on nitty-gritty details of data interpretation that don't meet her standards for a convincing detection. Her criticism reflects concerns that the Cambridge team may have pushed their analysis techniques beyond reliable limits while searching for extremely weak signals in noisy data. This skeptical response also draws on astrobiology's troubled history with false positives. Beyond the famous Martian meteorite controversy, the field has weathered multiple claims of biosignatures that later proved to result from non-biological processes or measurement errors. These experiences have made many researchers extremely cautious about accepting extraordinary claims without overwhelming evidence. Some critics argue that the Cambridge team's public announcement violated scientific norms by publicizing results before full peer review and independent verification. While the research appeared in a peer-reviewed journal, the dramatic press releases and media coverage preceded thorough scrutiny by the broader scientific community. The debate has intensified around fundamental questions of scientific methodology. Should potentially world-changing discoveries be announced as soon as they reach basic statistical thresholds, or should researchers wait for multiple independent confirmations before making public claims? The K218b controversy illustrates the tension between scientific caution and public interest in groundbreaking discoveries. As more research teams analyze the Webb telescope data using different methods and assumptions, the scientific consensus may shift either toward accepting or rejecting the biosignature claim. The ultimate verdict may require additional observations that could take months or years to complete. The fate of humanity's most promising lead in the search for alien life now rests on future observations that will either confirm K218b as a living world or relegate it to the catalogue of false hopes. The Webb Space Telescope team has already secured additional observing time to study K218b using different instruments and longer exposure durations. These follow-up observations could provide the crucial data needed to either strengthen the dimethyl sulfide detection to 5 sigma significance or definitively rule it out as instrumental noise. The stakes could not be higher. These measurements will determine whether we've found the first confirmed signs of alien life or encountered the most convincing false positive in astronomical history. The planned observations will employ Webb's full arsenal of spectroscopic instruments, including extended use of the mid-infrared instrument that provided the most compelling evidence for dimethyl sulfide. By observing multiple transits of K218b across its star, astronomers can build up signal strength while also testing whether the detected molecules remain consistent across different observations. One critical test involves searching for additional sulfur-bearing molecules that should accompany dimethyl sulfide if it's being produced and processed through biological mechanisms. The detection of dimethyl disulfide, hydrogen sulfide, or other related compounds would strengthen the case for genuine atmospheric chemistry rather than instrumental artifacts. Scientists are also developing more sophisticated atmospheric models to predict exactly what Webb should observe if K218b truly harbors life. These theoretical frameworks will help distinguish between biological and non-biological explanations for the observed chemical signatures, providing benchmarks against which future observations can be compared. The European Space Agency's upcoming Plato mission, scheduled for launch in 2026, will provide complementary observations of K218b and similar worlds. Plato's different observational capabilities could offer independent verification of Webb's findings while searching for additional exoplanets that might show similar biosignature patterns. Ground-based telescopes are also joining the effort to study K218b. The extremely large telescope, currently under construction in Chile, will have unprecedented resolution for studying exoplanet atmospheres when it begins operations in the early 2030s. This facility could provide detailed atmospheric maps of K2-18b, potentially revealing geographic variations in chemical composition that would support or refute the presence of life. Perhaps most importantly, astronomers are expanding their search to other similar worlds. If dimethyl sulfide detection on K2-18b represents genuine biosignatures, similar signals should appear in other Hycean exoplanets with comparable environmental conditions. Finding multiple worlds with consistent biosignature patterns would provide compelling evidence that we're observing a widespread biological phenomenon rather than unique atmospheric chemistry. The research community has also proposed dedicated space missions designed specifically for biosignature detection. These future observatories could study dozens of potentially habitable worlds with sensitivity far exceeding current capabilities, transforming the search for alien life from individual case studies to comprehensive surveys of nearby star systems. The timeline for resolving the K2-18b question extends from months to years, depending on telescope scheduling and the strength of future observations. Each new measurement brings humanity closer to answering one of the most profound questions in science: are we alone in the universe? The answer may be hidden in photons already traveling toward Earth from that distant world. K2-18 represents just the beginning of Webb's hunt for alien life, with dozens of potentially habitable worlds already queued up for atmospheric analysis that could revolutionize our understanding of biology in the cosmos. The TRAPPIST-1 system stands as Webb's most ambitious target for biosignature detection. This nearby star system harbors 7 Earth-sized planets, 3 of which orbit in the habitable zone, where liquid water could exist on their surfaces. Unlike the hydrogen-rich Hycean world K2-18b, these planets might possess thin atmospheres similar to Earth, Mars, or Venus, offering the possibility of detecting oxygen, ozone, and other biosignatures associated with terrestrial-style life. Webb has already begun atmospheric studies of TRAPPIST-1b, the innermost planet in this fascinating system. Initial observations revealed that this world lacks a significant atmosphere, having been stripped bare by radiation from its red dwarf star. But planets further from the star, particularly TRAPPIST-1e, F, and G, might retain atmospheres capable of supporting liquid water and potentially life. The telescope's target list extends far beyond TRAPPIST-1. Proxima Centauri b, our closest known exoplanet neighbor, at just over 4 light-years away, presents another compelling target for atmospheric analysis. This potentially rocky world orbits in the habitable zone of the nearest star to our solar system, making it an ideal candidate for detailed characterization with Webb's sensitive instruments. TOI 715b, a recently discovered super-Earth, offers yet another opportunity to study atmospheric chemistry in a potentially habitable world. At just over 100 light-years from Earth, this planet receives stellar radiation levels similar to what Earth experiences, creating conditions where liquid water oceans could theoretically exist on its surface. Webb's observational campaign also includes a diverse array of planetary types beyond potentially Earth-like worlds. Hot Jupiters like WASP-39b have already provided detailed atmospheric inventories showing water vapor, carbon dioxide, sulfur compounds, and complex cloud chemistry. These extreme worlds serve as laboratories for understanding atmospheric physics under conditions that don't exist in our solar system. The telescope is particularly well suited for studying sub-Neptune planets, worlds larger than Earth but smaller than Neptune, that appear to be the most common type of planet in our galaxy. Many of these worlds might be Hycean planets, similar to K2-18b, potentially harboring global oceans beneath hydrogen-rich atmospheres where alien life could flourish. Mini-Neptune atmospheres present unique challenges and opportunities for biosignature detection. These worlds often possess thick hydrogen atmospheres that could hide surface conditions while simultaneously making atmospheric observation easier due to their large-scale heights and strong spectral signals. Webb's systematic survey approach means that the K2-18b detection, whether confirmed or refuted, represents just one data point in a comprehensive study of exoplanet atmospheres. Even if this particular world doesn't harbor life, the techniques and technologies developed for its analysis will inform observations of dozens of other potentially habitable worlds. The next few years will see Webb's atmospheric studies expand from individual case studies to statistical surveys, potentially revealing patterns in exoplanet atmospheres that could guide our understanding of where and how life might emerge throughout the galaxy. Each new world studied brings us closer to answering whether life is rare or common in the universe. The confirmation of life on K2-18b would trigger the most profound shift in human perspective since Copernicus moved Earth from the center of the universe. For thousands of years, humanity has gazed at the stars and wondered whether we are alone. Every religion, philosophy, and scientific tradition has grappled with this fundamental question, yet we have remained trapped in a sample size of one, Earth being the only known living world in the cosmos. The detection of biosignatures on K2-18b could expand that sample size to 2, fundamentally altering our understanding of life's place in the universe. The philosophical implications would reverberate through every aspect of human thought. If life emerged independently on K2-18, it would suggest that biology represents a common outcome of planetary evolution rather than an extraordinarily rare accident. This realization would transform our understanding of cosmic significance from seeing Earth as a unique oasis of life to recognizing it as one example among potentially billions of living worlds scattered throughout the galaxy. Religious and spiritual traditions would face unprecedented questions about the nature of creation, consciousness, and divine purpose. Some belief systems might interpret alien life as confirmation of a universe designed to nurture biology, while others might struggle to incorporate non-terrestrial life into theological frameworks built around human exceptionalism. Scientific research priorities would shift dramatically toward astrobiology and comparative planetology. Understanding how life could evolve in the extreme conditions of K2-18 would require fundamental advances in biochemistry, evolutionary biology, and planetary science. Universities would establish new departments dedicated to studying alien life, while space agencies would prioritize missions to potentially habitable exoplanets. The economic implications could prove equally transformative. Technologies developed for detecting and analyzing alien life would likely find applications in medicine, environmental monitoring, and industrial processes. The space industry would experience unprecedented growth as nations and private companies compete to study potentially living worlds throughout the galaxy. Cultural impacts might emerge more gradually, but prove equally profound. Science fiction would give way to science fact, forcing humanity to confront the reality rather than the imagination of alien life. Art, literature, and entertainment would grapple with themes of cosmic citizenship and humanity's role in a universe teeming with biology. International cooperation in space exploration would likely intensify as nations recognize that studying alien life represents a challenge too large for any single country. The detection of life on K2-18b could catalyze unprecedented collaboration in developing interstellar observation technologies and deep space exploration capabilities. Perhaps most significantly, confirmation of alien life would provide perspective on Earth's environmental challenges. Seeing our planet as one of many living worlds might inspire greater efforts to preserve Earth's biosphere, while simultaneously offering hope that life's resilience extends far beyond our solar system. The psychological impact on individual humans remains difficult to predict, Some people might feel diminished by the realization that Earth isn't unique, while others might feel inspired by evidence that life can flourish under conditions previously thought impossible. Either way, the discovery of life on K2-18b would mark a turning point in human history, comparable to the development of agriculture, the scientific revolution, or the industrial age. We stand at the threshold of potentially the most important discovery in human experience. Whether K2-18b harbors life or not, this discovery has already rewritten the rules for how humanity will search for alien biology throughout the cosmos. The techniques pioneered in analyzing K2-18's atmosphere represent a revolutionary leap in our ability to study distant worlds. Webb's demonstration that we can detect specific molecules in exoplanet atmospheres across hundreds of trillions of miles opens possibilities that seemed like science fiction just decades ago. Future telescopes will build on these capabilities, eventually creating detailed chemical maps of potentially habitable worlds throughout our galactic neighborhood. The Hycean planet concept has emerged as a game-changing framework for astrobiology. Before K2-18b, most searches for alien life focused on Earth-like rocky planets in habitable zones. Now we recognize that hydrogen-rich ocean worlds might be far more common and easier to study than Earth analogues, potentially multiplying the number of potentially habitable worlds by orders of magnitude. Even if the dimethyl sulfide detection proves to be a false positive, the scientific methods developed for this analysis will inform future biosignature searches. The statistical frameworks, atmospheric modeling techniques, and spectroscopic analysis methods represent permanent additions to humanity's toolkit for detecting alien life. Each failed detection teaches us as much about biosignature science as each confirmed discovery. The international scientific collaboration sparked by K2-18b demonstrates how the search for alien life transcends national boundaries and political divisions. Research teams from universities across multiple continents have contributed to analyzing, confirming, and questioning the biosignature detection, creating a global network of scientists united by the common goal of understanding life in the universe. Future space telescopes already under development will dwarf Webb's capabilities for exoplanet studies. The proposed Habitable Worlds Observatory could directly image potentially living planets, analyzing their atmospheric composition and even detecting seasonal changes that might indicate biological activity. Ground-based, extremely large telescopes will provide complementary observations with unprecedented resolution and sensitivity. The K2-18b discovery has also sparked renewed interest in interstellar exploration technologies. While the distances remain impossibly vast for current propulsion systems, the possibility of confirmed alien life provides motivation for developing revolutionary space travel technologies that could enable robotic missions to nearby potentially habitable worlds within human lifetimes. Artificial intelligence and machine learning techniques developed for analyzing Webb's exoplanet data will accelerate future discoveries. These algorithms can identify subtle patterns in spectroscopic data that might escape human detection, potentially revealing biosignatures in worlds previously dismissed as lifeless. The next decade will likely see dozens of additional exoplanets analyzed for potential biosignatures, creating a statistical database that will reveal whether life is common or rare in the universe. This systematic approach transforms astrobiology from speculation into rigorous observational science. Regardless of what future observations reveal about K2-18b specifically, this world has already secured its place in scientific history as the planet that taught humanity how to smell the breath of alien worlds and detect the chemical signatures of life across interstellar space. The age of exoplanet atmospheric archaeology has begun, and K2-18b stands as its first great discovery. Our cosmic loneliness may be ending one molecule at a time,